Now that we've learned some terminology so that we know what vocabulary to use as we discuss these different compounds that we are studying, let's go back to our molecular compounds. Okay, that's what we've been working with our Lewis dot diagrams, and that's what we're going to start our focus on. Molecular compounds, meaning they are covalently bonded, which means that they are sharing electrons between nonmetals. Okay, so we're going to learn how we can just look at a chemical formula and know the name of that compound. Now, chemists who have been working in the chemical field for years and years and years, they do this naturally. They can just look at a chemical compound and instantly know its name because they've been working with it for so long. But for all of you, you're just getting started with nomenclature, naming of these compounds. So for you, it's going to take practice. You're not going to instantly know the name when you see it. You're going to have to work through the rules that I'm going to go over for you. But the great thing is there is a specific set of rules. So once you learn those rules, you can apply it to every single chemical compound you come across to be able to correctly identify and name it. Okay, and we're going to start by naming molecular compounds, compounds that are bonded covalently. So let's start by talking about bonding energy. Okay, so potential energy, remember, is the energy stored within a compound. It's the potential to release that energy. It's stored in it. Okay, this is going to be based on the position of an object, and low potential energy for a compound means high stability. So if there's very low potential energy, that's a very stable molecule. Okay, so let's take a closer look at this bond energy graph. Okay, all right, so what we have is an attraction versus repulsion based on how close together the two nuclei are. So on this graph, if you look on the side here, we have the potential energy. Remember, low potential energy means high stability. And we're studying hydrogen nuclei. So here we have the distance. Okay, so right here in the beginning, this is a very low distance for the nuclei. They're very close together, and they have a very high potential energy. Why is that? Because the nuclei are positive, and the like repel. So at this point where the two nuclei are very close together, those positive nuclei are very close together, they have a high repulsion. They are repelling each other. They're pushing against each other. So that's where that high potential energy is, because they have that pushing. Okay? Then as they push apart, they reach a very high stability point where the positives are far enough away from each other that they are not repulsing each other, and they have a high enough attraction that they're not pulling each other together, but they're able to share their electrons so that they can have that full outer valence shell. So this is where they are happy. There's very low potential energy. There's not a lot of repulsion. There's not too much attraction. But then if the atoms continue to move apart, what we see is the potential energy increasing again. Because at this point, now they have high attraction forces, and they're trying to pull towards each other to get closer together. But if they continue to move even further apart, you're going to reach a point where there is no attraction anymore. And there's no interaction at all, because they're so far apart that they can't even have that attractive force. Okay. So this area between my two green lines here, this is the amount of energy that is required to break the bond. Okay, that is the amount of energy to break the bond. So let's get into molecular nomenclature, naming these covalent molecules. We are going to use a prefix system. Okay, now this is for binary compounds, meaning there's only two different types of elements. Okay, so when you are given the two elements that are in your compound, the less electronegative atom comes first. Okay, the less electronegative atom comes first. We are going to add prefixes to indicate the number of atoms in the compound, with one exception. On the first element, if there's only one, you don't do mono on the first word. Okay? You do use mono for the second word. You do not use mono for the first word. All other prefixes get used on both words. Okay? And I'm going to do some examples to show you this. Okay? And then the third step of naming a molecular compound is you change the ending of the second element to IDE. Ide. Okay? So let's do some examples. Well, let me give you your prefixes first. That's good. Okay, so here are your prefixes. Make sure to add these into your notes. So we use the prefix mono for 1, di for 2, tri for 3, tetra is 4, penta is 5, hexa 6, hepta 7, octa 8, nona 9, and deca 10. You've probably heard these prefixes before in a math class or a geometry class, counting the sides. Dungeons and Dragons players have heard some of these before because of the specialty dice. Okay? Alright, so those are the prefixes that you're going to use for your numbers of atoms. Now let's do some examples. Okay, CCl4. Okay, so we're going to look and see. The letter C stands for carbon. So I've got carbon, and Cl stands for chlorine. Okay, so we've got carbon, chlorine. Now, there is no number, there is no subscript for C. That means that there is only one carbon. Okay, we do not use the prefix mono for the first element, so we're just going to say carbon. Now, for the next one, we have 4 chlorines. So 4 is tetra, so it's tetrachlorine. But then that last step, we have to change the ending of the word from chlorine, change it to IDE, so it becomes chloride. Okay? Carbon, tetra, chloride. All right, our second example here, N is for nitrogen, O is for oxygen. Okay, and that's fine if we're using our periodic table to look those up. Hopefully some of these are starting to become you're used to them. We're seeing them all the time. They're starting to be committed to memory. So we have 2 nitrogen, so that becomes dinitrogen. Second one, there's only 1 oxygen, and it's the second element, so we are going to use mono, and we're going to change the ending to ide. So this becomes dinitrogen monoxide. Okay. S is for sulfur, F is for fluorine. We have 1 S, but that's the first element, so we're not going to use mono, so that's just going to be sulfur. And then there are 6 fluorines, so hexa, and then we're going to change the ending to IDE. Sulfur hexafluoride. Okay. Nice and easy, right? Just got to practice. And soon you'll be able to just look at an element and go, oh, or look at a compound and go, oh, I know your name. And we can do it in reverse too. So if I give you the molecular name, you can give me the molecular formula. Okay, so we're going to look at our periodic table and we're going to find arsenic, and we're going to say, okay, what is arsenic? It is AS. There is no prefix in front, so that must mean there's only one of them. And then we have trichloride, So chloride would be the chlorine, that is Cl, and it says tri, so that means we have 3 of them. So it is AsCl3. Dinitrogen, okay, and nitrogen is N, di means 2, so N2. Pentoxide, so oxide is going to be oxygen, pent is 5, N2O5. Tetraphosphorus decoxide, okay, phosphorus is a P, tetra is 4, oxygen, and deco is for 10. So P4O10. Okay, the last thing I want to talk about today is the diatomic elements. There are 7 diatomic elements. These are elements that are never found as a single atom. They will never be alone in nature. They will always be paired with some other element, even if that just means it is paired with another atom of itself. So if you ever write them alone, you'll never write just O, because they'll never be just oxygen, right? It will always be O2 when it's by itself, okay? Now, you can have just one O, like CO is carbon monoxide. There's only one O, but that's because it's not alone. It's paired with carbon, okay? You'll never have it absolutely alone. It will always be paired with something, even if it's just itself. And you do need to memorize who the 7 diatomic elements are. And the great thing is, I think it's easy for me to remember because they make the number 7 on the periodic table. Nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. 7 plus hydrogen, because you know hydrogen is an exception to so many rules, and hydrogen's the exception to the number 7 rule as well. Okay, so 7 diatomic elements, they make a 7 on the periodic table plus hydrogen. If you are not able to name those compounds as I went through the examples, if you have no idea where I was getting those words or those numbers, please get into contact with me so that I can help you, because what's next is some independent practice.